Shall we start?
Yeah.
So let's start our OCAMI colloquium. So today's speaker is Travis Scrimshaw from Hokkaido University, and he's going to talk about combinatorics observable lattice models. Please start.
So, thank you very much for having me. If you have any questions, 質問があれば日本語で切っても大丈夫ですけど、その講演は英語で行います。So, if also I'm speaking too quickly in English, please let me know. Please interrupt me. If you don't understand something, I can try and translate it. Please, use this time to ask me questions. And I may not turn around so much, so that's why I tell you, please interrupt me if you have any questions. So,
sorry, I forgot one more thing. So, this to say, colloquium session is recorded, and could possibly it would be uploaded to YouTube. So if you make some question or something, so please allow us to record those voices and so on. Thank you.
So our starting point is water, mizu. Well, actually not really water. We want ice, kaori, because we want to consider this to be, at the end of the day, we're going to consider things to be really, really cold. In fact, we're going to go to absolute zero temperature, where nothing moves. That's going to be more or less our end point, but we're going to start with things being actual positive temperature where they can move around a little bit. And, well, if we really think about water, at some point, I hope, since I have colors, let me use colors. You've learned that water is 2 parts hydrogen and 1 part oxygen, and they have a very special bond between them. And then oxygen, well, it kind of has these 2 extra parts attached to it, where due to how electrons and the bonding works, maybe you don't remember this, but essentially there's a bit of a pull in one direction. One part is more negative than the other side. So for oxygen, I'm drawing this in 2 dimensions, but really it's kind of in 4 dimensions. 3 dimensions, and it's 4 points of a tetrahedron. That's not fully correct, but that's good enough of an approximation. The problem with this is it's too complicated. Putting things in 3-dimensional space is hard. Even understanding how spheres put together is a hard problem. So let's not do 3 dimensions. Let's look at a toy model in 2 dimensions. And so when we go from our 3D picture here down to a 2-dimensional picture, well, the hydrogens and the extra little pluses part, the empty parts, they want to kind of spread out. And so locally, what this will look like is, if they want to be kind of as far apart and repulse each other as much as possible, in 2 dimensions, you're going to get a grid, a square grid, where at every point you may have a hydrogen, and then you'll have one of these kind of empty spots here. So to not have to draw hydrogen over and over again, what I'm going to do is I'm going to simplify this picture, but let me draw just a little bit more to indicate kind of how this is going to work in general. So I'm putting things together in this grid. And then every oxygen is going to have some hydrogens associated to it. And it's going to have 2 of them. But if there's a hydrogen here and a hydrogen here, they're going to repulse each other. They want to move as far apart as possible. So this, putting an extra hydrogen here, that's not going to happen. Instead, we're going to have a hydrogen here, and, well, this is going to want to put a hydrogen here, and let's say we put the hydrogen here, and, well, similarly, the 2 extra parts are going to want to repulse each other. They're going to want to move as far apart from each other as possible, so in this gap, we must have a hydrogen as well. And similarly in here and say out here. So this is a local configuration. I'm not doing anything special on the boundary components, but I will in a second. However, this is what my general configurations will look like. And to simplify my picture, what I'm going to do, well, there's essentially kind of an orientation attached to each of these, basically telling you about the how the charges are associated. So now if I do this in this picture, other way, excuse me. My picture transforms into, I take this square grid and now I put arrows on it. So I'm abstracting it away. I'll do a little bit more, move a little bit more away from kind of the physics in a second and actually make it a more mathematical picture. But essentially what I'm doing is I'm saying there's 6 possible configurations here. Because the hydrogen, I must have 2 choices for hydrogen around an oxygen, and 4 choose 2 is 6. So we see that I have, and that, translating this into this arrows picture, I now have, I'll always have 2 arrows coming in and 2 arrows coming out. I should be more systematic about this, so I don't accidentally miss stuff. And finally, here are my 6 configurations. So and what we want to think of this as is, we want to assign weights to these. We want to say how likely it is to see one of these states. Now, in water, probably in this model, a state like this will occur less frequently than one where the hydrogens are at an angle, are kind of closer to each other because of they want to be more like 104 degrees. So, but in general, like I want to be a mathematician, I don't want to be a chemist, and so I want to put an arbitrary probability to each of these. And up to normalization, I can ignore an overall factor. Like there will be a total sum that I divide by. I'll have my 6 configurations with weights A1, A2, B1, B2, C1, and C2. They'll sum together to something that may not be 1, but I can divide by that value and get an honest-to-goodness probability. And more general, I can do this to an entire grid with maybe some fixed boundary conditions and divide by it. But I'm not going to do probability theory, so I'm not going to care about that. But if I was doing something more physics, chemistry based, I want to find out questions like what's the probability of certain configurations. That's a different question that I'm going to talk about today, but this is the difference that you might see if you look up these things in the literature. So the other problem with, or a problem with this is it's not clear that I have 6 configurations. Like you have arrows, and I look at this, and I'm pretty sure I've done this correctly. But I'm still pretty sure. I'm not 100% sure. So let me use a different picture. My picture now is I'm not going to care about the arrows. I'm going to have, what I'm going to think about is I'm going to have particles that come in to this point, they interact in some way, and then they separate. And I'm going to have, I want a balance condition because I don't want matter to be created or destroyed. I know I'm still talking like a physicist here, and I'm not yet a mathematician. Please bear with me. I will get there. So let me first say no particles comes in, so no particles comes out. Okay, good. Now I have 2 particles coming in and 2 particles going out. There's no ambiguity there. Now I can have 1 particle coming in, and let's say it just travels straight through. I can have 1 particle coming in, it travels straight through. And then I can have these kind of, well, they don't travel straight through, they come and bounce off each other. So how I'm thinking about time is moving in this direction. So the 2 particles come in and, well, cross, bounce off each other. We don't care. They're the same particle. They're indistinguishable. So now you can check very easily that I've actually given you 6 configurations with respect to this balance condition. That the for a general state like this, the number of incoming must be equal to the number outgoing. So I'm translating it a little bit, but it turns out this is actually a much easier thing to work with because now I can talk about vector spaces. I can take a two-dimensional vector space and take a tensor product. But just to keep things extremely simple and pictorial, I'm just going to write it once and then we'll forget about it. But essentially what I have is a matrix that goes from, that describes C2 tensor C2 to C2 tensor C2, where this vector space I have E0, E1, and E0 represents no particle, and E1 represents a particle. So, I have a balance condition. I don't, this is a four-dimensional vector space to a four-dimensional vector space. It's a linear map, and there's 16 entries, and I say all but 6 of them are 0 because I want this balance condition. And if this was a more specialized talk, I would say more about the fact that these are quantum group representations, but I'm just going to say fancy words and move on because we're not going to care about that. Instead, what we're going to do is combinatorics. We're going to count stuff. And the first thing that we're going to look at is the following, so let's take C2 to be 0, and we'll take A1 equals A2 equals B1 equals B2 equals C1 equals 1. So basically, by setting C2 to be 0, I'm saying this doesn't appear. And by setting these weights to be 1, I'm going to say all of these count the same. So I'll explain more in general what happens when I actually make things not 0 and not 1, but right now I just want to count stuff, so this is more for future reference. So we're just going to ignore the weights for right now. And so what I'm going to do next, actually let's go one smaller. Is I'm going to have boundary conditions that say particles come in on the left and exit at the top. No particles come in at the bottom, no particles exit on the right. And all I want to do is count the number of states that are possible. So now I'll draw this just a little bit smaller to so I can count things a little better. All right, so this first entry, I'm just going to draw in my lines just to start, and we'll fill in the rest of these in a second. So essentially, if I actually gave these particles names and said that they always bounce off each other, they never cross, you can see a little bit more of what's happening. Unfortunately, I don't have 5 or 7 marker colors to do this properly, so I'll try and connect the lines up as much as possible. So if I can have this second particle I have the first particle, it always just goes up. There's nothing it can do because these particles never cross each other. So it's always 1, 1, 2, 2, 3, 3, like this. So the second particle can just go over, and let's say the third particle comes up and over. Let's keep the second particle going the same, and now the third particle can do something a little more interesting. And now we've exhausted all possibilities with the second particle coming over and up. So now there's only one other possibility for the second particle, which is to go up over up. And let's just do this systematically. This particle comes over like this, and now I can flip this up by 1. I can make it go up and over, and finally it can step over 1 and then go up like this. So there's 6 possibilities here. And now what I'm going to do is I'm going to look at these corners. And I'm going to put a 1 at each of these corners. Oh, sorry. This one's bad. I want to hold on to it, but let me redraw it over here. Yeah, this is the last one I'm missing, but I also had this one here. But this one is bad because of this. I've said this is 0. So this doesn't appear. And I'll come back to this in a second. So here I have, I'm just labeling these corners by 1. Does anyone notice something about these 1s? And maybe if I put 0 for everything else, it would be more clear. I know it's a little hard for people in the back I may be writing a little small, and I'm sorry about that, but I claim if you give this to a first-year linear algebra student after they've learned Gaussian elimination, they will know what these are.
Like permutation matrices.
These are permutation matrices, exactly. So I've built a bijection. I claim that this holds true in general, that I have a bijection between configurations if I use only these 5 local configurations, with the left boundary being particles entering and the right and top boundary being particles entering, that the corners, the C1 configurations, if you put a 1 there and a 0 everywhere else, you get a permutation matrix.
Can I ask a question?
Yes.
Maybe I don't understand how you correspond the second line from the first line, I mean on the left. And for example, if I look at the first line, it is possible to place B1 and A1. A1 is on the right to B1.
I didn't do this very well.
Oh.
There is a correspondence. I didn't bother figuring it out because I always screw it up. And there's convention choices, but there is a way you can make this actually consistent. I should have said that. I'm not saying these correspond to each other. I'm just counting them. There is a way to do it, but I'm being very bad here.
Okay, thank you.
That being said, if I allow this, if I take C1 to be 1, and if I write -1 here, and put 1s and 0s, like this bad configuration. Now I'll write it as an actual matrix. This is what's known as an alternating sign matrix. What it is as I read along rows or along columns, the entries, the non-zero entries alternate between +1 and -1, and they sum together to be 1. And there was a big conjecture in algebraic combinatorics that asked how many of these are there, where it had a nice factorial product formula. That was the conjecture. Zeilberger had a 92, 94-page paper with lots of intricate combinatorics and proved it. And then about 1 month later, Greg Kuperberg said, well, there's this bijection. Physicists know how to count these things by actually taking these to be, it turns out that the physicists, they said, well, we can't just actually count these. The formula that we have, these are related and given by a single parameter q, and then at q equals 1, this formula is actually, it's a singular point. So you need to be careful about the limits, but Kuperberg massaged it a little bit and showed that it precisely gave this conjecture, and the paper was 10 pages long. So he's relying on some other work in the math physics community, but essentially, it becomes a very simple formula. So this is already kind of a hint. This is not the first instance of kind of a way to count stuff using these lattice models, but this is the easiest way I can explain without motivating too much that we can count stuff. And we can see very easily how this works. So now let me talk a little bit about the more general case. So we have some model where we specify maybe some boundary conditions, and we have some state, which is basically the local configurations by assigning either 0 or 1 to each edge. And an edge, for example, we have an edge. These are examples of edges. Like anytime you have a crossing, it's a vertex, and then you have boundary points as well. And so you have these kind of exterior boundary edges. But the reason why I distinguish the boundary edges is because typically we impose some boundary condition. So I'm formalizing just a little bit more what I was doing over here. I'm saying each of these blues is a 1 and a black without a blue is a 0. And I'm assigning one of these. And then, okay, I have a bunch of local configurations. And the weight of a state is equal to the product of the weights of each local configuration. And the product is over all crossings. So for example, if I take this state here, I have 4 places. This is a B2, this is a B1, and these are both C1. So the weight is B1, B2, C1 squared. So in particular, if a weight is 0, if a local configuration weight is 0, then the weight of the state will be 0. And so that's why setting C2 to 0 means I can't have this state in here. And I could generalize this to look at every possible one of those 16 local configurations that I get to fill that 4x4 matrix. And like I said, most of them are 0. So if I have a state, a local configuration that looks, say, something like this, I can say just the weight of this is 0. So, okay, let me bring back just a little bit more linear algebra. These bigger configurations is just basically a big product of these 4x4 matrices. And I take particular inputs and particular outputs. That's the, if you want a less pictorial, more algebraic way of explaining this, that's what I'm doing. So now let's do something with the weights. We don't want to just count stuff. We want to count stuff with weights. And so the weights that I'm going to use basically for the rest of the talk are as follows. So, okay, I'll draw it in and then I'm going to cross it out because I want this to have weight 0. This will have weight 1. I will say what z means in just a second. So everything else will have weight 1. And the model that I'm going to work with will have no particles entering from the bottom or exiting on the right. I will have particles entering on the left. And let me draw one additional line in here. Let me draw a few additional lines in here. And then I'm going to have my particles exit at the top with some fixed lambda configuration. So let me draw lambda in a more convenient way. So what I'm going to do is I'm going to read it from left to right. And every time I see a hole, I'm going to start at some point down here. And basically, the number of vertical steps, I'm going to do some horizontal steps and some vertical steps. And, well, I can start at the point where the number of vertical steps I'm going to do is going to be the number of particles, because every time I see a particle, I'm going to step up, and every time I see a hole, I'm going to step to the right. So in this, the first thing I see is a hole, so I step right. Then I see a particle. I'll just label these 0 and 1. Then I see hole, 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 particle, particle, hole, particle, and then there's kind of an infinite number of holes off to the right. I can always add a column with 0 at the bottom, 0 at the top, and 0 at the right, but that makes no difference. The interesting stuff happens in this part. And so now I complete the picture in the following way. And this is known as the Yang diagram of the partition mu. So, let me say of the partition lambda. And so I can write lambda as 5, 4, 4, 1, just counting the number of boxes in each row. And then the positions of the particles are lambda I minus I plus 1 with an appropriate shift. And the shift is going to be, let's see, what's my shift? So if this is 0, then 1, then my shift in this case will be L, where lambda is lambda 1, lambda 2, up to lambda L. Maybe that's one base, but whatever. This extra shifting part here isn't terribly important. The minus I is what takes you from something that can have repeated things to something where they're always disjoint. And the extra shift is whatever I want to call 0. Wherever I want to put my origin, thinking of this as Z. But it's that part's not really consequential. So, all right, I have this. And now I want to write some local configuration. No, that's not going to work either. All right, this is a bad example. Let me make the example just a little bit better here. So here is a perfectly good configuration. And then I'm going to attach to every row a parameter. I'll call it x1, x2, x3, x4. And this is what the z is. So if I look at, say, the third row here, anytime I see this configuration, it's going to have, so this will have a weight x3. Here's an x3, here's an x4, x4, x4. Here's another x3, x3, x2, 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 x1, 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 like this. So the weights here, all other configurations have weight 1, so my weight is x1 to the 4, x2 cubed, x3 to the 4, x4 cubed. This is the weight of this state. And now what I'm going to do is I'm going to sweep my way up from top to bottom. And I'm going to make a cut here. And I'm going to do this exact same translation to a Yang diagram. So if I restrict myself to the first row, so here, this L is going to change. I pick an origin, but whatever that L is, it's going to change as I move up because there'll be more particles. So if I call this 0, then the 0 kind of moves. And so you have to be just a little bit careful with that translation. But let me just do it, and you'll be able to see. So I'll write it lambda upper 1 is just 4. And then lambda upper 2 will be 4, 3. Lambda upper 3 will be 5, 4, 2. And then lambda upper 4 is my original lambda here. So now, let me wish that I had more colors, but so be it. So let me fill in up to lambda 1 with 1s. Now let me fill in the new boxes that I see between lambda 1 and lambda 2 with 2s. And similarly, now I do with 3, so I have 5, 4, 2. And finally, the remaining boxes get filled in with 4. And there's something that happens in general for a single row. So I take a single row of my diagram, and I have lambda, a configuration lambda and a configuration mu, and they have there's a Yang diagram, and I'll pictorially, I have this bigger shape lambda and this smaller shape mu. And the first thing is that they're contained inside of each other. But if you look at their difference, the part that remains you see that it ends up being only a bunch of horizontal strips. So basically what this comes from is the fact that this never occurs. So when you have corners touching like this, I have at least I can use a little bit of different colors. This corner comes from this local configuration. This endpoint comes from this local configuration. This start point comes from this configuration. And finally, things in the middle are this local configuration. And so you may have to do like 3 examples, but you can convince yourself that there's this correspondence fairly easily. So what we get as a result is a bijection. Between states of this lattice model and combinatorial objects called semi-standard Young tableau. And because it's French, there's a silent X at the end. That means plural. Ask maybe Miyachi-sensei for why the French do this, because he knows French and I don't. This is probably why I don't know French. And so what these, I can give you very precisely what these are from this rule. They're fillings of the boxes of the Young diagram and this picture has to go away, and I'm sorry, but I will at least keep this picture up. With entries 1 to up to n, where this is the number of rows, such that columns strictly increase from top to bottom, and rows weakly increase from left to right. And so we can see this here. 1 is less than 2 is less than 3 is less than 4. 1 is less than 2 is less than 3. 1 is less than 2 is less than 4. And then as we read left to right, we also get the same behavior. And this is just a consequence of what it means to add a horizontal strip. You start with a shape lambda, you go to a shape mu. The difference is you start with a shape mu, and you go to a shape lambda by adding a horizontal strip. That's the only thing you can do. And you fill in those boxes with, the next step that you're doing. And hence, well, you get precisely this condition here. Columns have to increase because it's horizontal strip. You have no vertical dominoes appearing in the shape. You basically, horizontal strip means you don't see any subdiagram like this. And that's the column strict condition. And then the row condition is, well, you're always you're growing it. So that's the increasing condition for both of them. But yeah, so this is the strict condition. So this is good. But what does it give us? What does solvable mean in my title? So the theorem is this is solvable, which means there exists a tilted version where we have the same kind of behaviors happening. We read kind of this direction now. It's still kind of this direction, but maybe just ever so slightly tilted down. So both cases make sense for how to read it. And we have, again, a particle conservation. As I read from left to right, the number of particles coming in is the same as the number of particles going out. And these will have some weights, R1, R2, R3, R4, R5, R6. Such that the Yang-Baxter equation holds. And then for maybe more experts, this is, or if you go look this up, this is what's known in RLL form. So I'll explain what this means right now. So I have A, B, C, D, E, F. I have these boundary points. And then over here, I have these boundary points. And the Yang-Baxter equation says these are the same model in the following sense. That if I sum over all states, and let's call that state S, and I look at the weight of the state over here, this is the sum over all states S prime, and the weight of the state over here. So this is a local criteria, basically. So the reason why this is called RLL is because in the literature, this is known as an R matrix. And what I told you before is known as an L matrix. So there's an R matrix, an L matrix, and an L matrix. And here we have an L matrix, R matrix. So linear algebra. All right, it looks like this. I mean, I'm being very hand wavy here because secretly this is now a threefold tensor product, and the factors that things are acting on matter here. But this is what the Yang-Baxter equation is saying, is that if I take these two vertical pieces here and attach this R matrix, it's the same as what I get on the other side. But there's actually a little bit more information going on here because I have a parameter x and a parameter y. So the y comes up here, the x is down here. This is the same x, same y, but now the x and the y are changed. So passing this, basically what the Yang-Baxter equation says is that if I attach an R matrix and I can bring it to the other side of two of these L matrices, these two local configurations that we're working with using this tilted one, and it interchanges the two. It's basically playing the role of a simple transposition. So I claim that for this model that I've described, there's some R1, R2, R3, R4, R5, R6 that makes this equation true for all fixed boundary conditions. So this is true for all fixed A, B, C, D, E, F. So what does that give me? Well, let's consider two rows. And this is labeled by xi and xj. And then I attach my R matrix to it. So, I have some, and I still have my fixed boundary conditions 1, 1. And because the particles must be conserved, I still have 1, 1 coming out on the other side. That's my particle conservation. And over here I have 0, 0. Maybe I'll, actually I can write that in blue just to be consistent with my colors. That. So in my convention here, what I'm multiplying by is an additional R4, and then let me call it Z, X, J, Xi. This is my, to give it a name, I'll call it the partition function. That's this sum over the states. Weight S, S, a state. So I can use the Yang-Baxter equation to say that the partition function of this model is equal to the partition function of this model. But now this is xj, xi. This boundary condition is still 1, because again, it's true for any boundary conditions. And, and these boundary conditions are 0, excuse me. But I'm allowed, here and here, these two boundary conditions, what I have called over there C and D, they're free. They can be whatever I want. I'm summing over all such possibilities. And I'm still doing the same here. And I can repeat this until I get my same lattice model but now with xj above xi, and then I have my Yang-Baxter, or my R matrix over here with 0, 0. And this gets me a R1. And I will claim that R4 equals R1. That's true by this theorem. I know I'm out of time, so I'm going to just move very, very quickly with the final statements here. That the partition function is a symmetric function is a consequence of this. And, well, we know that the partition function is a sum over the weights of the semi-standard Young tableau. Let me call it T. T, a semi-standard Young tableau of shape lambda, and where this is just the x1 to the number of 1s, x2 to the number of 2s. Etc. So this is a symmetric function, and it has a special name. This is called the Schur function. And then it turns out if we color the particles, we get a similar story, but now the particles bounce, particles that cross each other versus bounce off each other are different because now we can distinguish them by their color. And it turns out what you get, I guess I would attribute this to Bushmash, Bump, Brubaker, and Gustafsson from, I want to say, 23. I might be slightly wrong about that year. And then also Valentine and I with Katie Weber made this explicit in a slightly more general setting, but from what Dan Bumpus told me, they proved it. They realized this about the same time, but that this encodes a kind of partial version called key polynomials. Which I'll call kappa w lambda, where one case is x1 to the lambda 1 dot 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 xn to the lambda n, and the other is the Schur function. And by an explicit functional, relation. So this essentially gives you a combinatorialization, this colored version of what I'm talking about for these key polynomials, also known as de Mazur characters. So I'm over time, so I think this is where I'll end. Do you have any questions?
May I ask one question? So, one or two. Say, at the beginning you said that temperature absolute zeros. So, what does this mean?
So I passed by it without saying it. So Kuperberg, that's Q to 1. So Q to 0, I ran out of time, but there's another system that's described by a similar dynamic with the full 6 local configurations that involves a parameter Q. And when you send Q to 0, what happens is that's like your temperature going to 0, and it defines a dynamical system, a discrete dynamical system called the box-ball system, where you have bins that contain balls, and what happens is the rule that you get for this is you start from left to right and you sweep along, and every time you see a ball you pick it up, and every time you see a hole you drop it down. So you pick up, pick up, pick up, drop, pick up, drop, drop, drop. And the Q to 0 limit precisely encodes this dynamic here. And you end up, if I want to be very precise about this, well, if there's nothing, you do nothing. If you see a ball, you pick it up. And if you have a ball, you drop it. And then, well, this kind of extra one is if you're already, what ends up happening is you have really, how this works is you have a kind of fused version of it. This never actually occurs. So, I'm out of time, so it'd take me another like 5 to 10 minutes.
Okay.
But essentially, it shows up in this dynamic here.
And another one is, seems to me that somewhere those representation theoretic background, then those standard, semi-standard tableau sounds like weight spaces somewhere. So those your configuration is somehow connected with weight spaces, right? Not really.
Yes, but it's less direct than you may expect. I would have to say the words boson-fermion correspondence and Clifford algebra, but that's the connection, that the single row of this vertex model, it corresponds to a half vertex operator or an exponentiated Hamiltonian with respect to the boson-fermion correspondence. That's the precise connection, and I'm happy to explain it to you when I'm not going to run to the airport.
Right.
But there is a connection, but it's not direct because really these local configurations are they're representing in general, maps between finite dimensional representations of affine quantum group representations without derivation, if I'm throwing fancy words around. But I mean, that's why I keep saying matrix and tensor product earlier, but that's a very different representation theory than the Schur functions and the GLN representation, kind of finite dimensional, finite, simple Lie algebra GLN representation theory.
I see. Somehow beyond my imagination, so thank you. So perhaps the time is running out, so let's stop at here, then let's thank the speaker. Thank you.